So this is about high resolution processing. We actually discussed beamforming last time. I'm going to go through at least one form of adaptive beamforming. And these are all actually adaptive beamforming using different ideas. But I want to get to the so-called super resolution or super resolution methods based on the eigenvector of the covariance matrix. So as I said, instead of one receiver, we have multiple receivers. And so sensors, wherever, distributed sensors, that's what it comes up to. So this could be a vector distance, some distance d1, d2, etc. It could. So d1 could be from here, d2 also could be from here, etc. So whichever way you measure the delays. And last time we went through this. If you have two sensors and you have a narrowband signal coming, the important thing is this wavefront is going to hit here first, then the same waveform is going to come here later. So if this is S of t, a bit later, at this time what you have is st minus tau, a delayed waveform. Delay is based on this distance. So if this is theta, and if this distance is d, then this will be theta, so that this will be d sine theta over c. That's the delay, right? So this will. So if st happens to be narrow band, e raised to j omega naught t, this will turn out to be e raised to j omega naught t minus tau. We went through this. So this is e raised to j omega naught, e raised to minus j omega naught tau, right? So omega naught is 2 pi f. F is what? C over lambda. And tau is d sine theta over c. So c cancels. And if you write the d over lambda, which is d over lambda by 2, then you can see this additional phase difference is, if you normalize with respect to lambda by 2, then this is just sine theta. So you can see in a narrowband scene, what I'm trying to say is every waveform at different sensors is going to be a phase delayed version. That's all right. So this is e raised to minus j multiplied by st. Compared to here, what you have is a phase delay. So the beamforming idea is that if it is just a phase delay, if you multiply by the complex conjugate of this phase delay, this will become s of t. If you add s of t plus s of t, you get 2s of t. And if you do this at m sensors, you can coherently add the signal. That's the idea. This is in an ideal world where there is no noise and where there are no interferences. And so question is, if you have an interference, and I showed you if you use this simple phase delay, so here the phase delay is depending on the sensor, you're advancing the phase by the complex conjugate of this. So if this is a numerical value I, in other words, it's a multiples of lambda by 2, then that becomes uniform phase shifting or steering the array to a particular direction. So essentially you come with a beamform. So the idea of forming putting a weights, you could say, is to form a beam. Then you get the idea. You want the main beam to be as narrow as possible and the side lobes to be as low as possible. So that itself is a big, lots of papers on that. How to put here non-uniform weights so that the side lobes are as low as possible. And I went through the general beam pattern for the uniform weight. So a uniform weight would be each of these sensor outputs is shifted and added. So it is going to be e raised to j I sine theta, right? I from 0 through m minus 1, depending on the number of sensors. And you can call this to be the gain pattern. And we saw that it's main lobe and peak side lobes we discussed. If you want to put additional weights, this is what you are going to do. You want to insert some weights here. The question is, what are the weights which will suppress the peak, peak side lobes, etc. Now, another way you could approach this problem here, so in terms of beamforming, we looked at the weight vector was simply A of theta. Remember, A of theta is the so if I define omega to be pi sine theta for easy notation, then this becomes e raised to minus j omega, e raised to minus j2 omega, etc., e raised to minus j m minus 1 omega. This is called a steering vector. The norm of this vector is m, so if you divide by square root of m, you get a normalized steering vector if you want. So of course you can see the output is you complex conjugate these weights and multiply by, so you can write this as in this fashion, right? Here x1, x2, etc., xn. This is w1 star, etc., wm star. So you can write it as an inner product w star x of t. That's the output. So if you look at the output power, that's expected value of y of t. Why I am writing theta is because you could assume that for some reason where we took the weights which are good for a particular direction, theta. And so if you, I think we were here, so this is expected value of, remember this is a scalar quantity, so this is scalar. Its absolute value square is multiplied by its complex conjugate. So this quantity multiplied by its complex conjugate is this. And the stochastic aspect is here, expected value is on this. So expected value of this quantity is what we call the covariance matrix. So remember that is whatever is the size of the array, m by m. So usually it's a positive definite matrix. So in beamformer, this is beamformer, W is A of t and the output is, so simply W, so W is going to be A of theta, so A star of theta Rxx A of theta. So that's the steering vector, electronic steering or, so there is no mechanical steering, you just change the weights to zoom in. So what we are doing is in space, we are zooming into a particular direction, right? So you can change this direction to somewhere else by steering the weights here. So you don't need to rotate the antenna. So the philosophy here is adaptive means usually it's not, of course if it is a single source, you can see the expression here. So if a single source is coming, then x of t itself is of this form, right? Yes, you get the idea, right? A source is located along the direction theta naught. So by the time, we went through this, right? By the time it comes, the signal will be, the signal phase shifted by e raised to minus j theta naught, because it is coming from direction theta, 2 theta naught, 3 theta naught, etc. So if you stack all of the x of t for a single source, it will look like this, plus noise. So the covariance matrix here is, I'll do the single source now. I'll give you the homework as two sources. The two sources I'll give you as a homework for you to plot it. So look at here. There's only two terms, right? Signal and noise are uncorrelated. The stochasticity is here. There is nothing stochastic here. So this is simply expected value of st squared multiplied by a theta naught, a star theta naught. This is a matrix of rank 1, right? Plus expected value of n star. This is also a matrix of, but if you assume the noise to be This is RNN, the covariance matrix of the noise. The simplest noise is assume that sensor to sensor, it may be true, maybe not true. Sensor to sensor, the noise is not correlated, uncorrelated, but they also have equal value. Again, it may not be true, but if it is true, then you have that ideal. So RNN is otherwise, of course, along the diagonal, you could have different values also. So all those will be a little more complicated cases. So I'm saying another case is RNN. Of course, this is full rank. So this has got entries R11. This will be completely correlated noise. The next best case is this one. It is uncorrelated but different variances. And the third case is all the variances are equal and uncorrelated. So this is what I have picked up to write. So if you plug in this, and this is going to be simply the signal power, so I'm going to call it P. What is it?
So S of t, we are assuming it is e raised to j omega naught t.
What is it? S of t? Yeah, as I said, I'm assuming it may not be. It's a narrow band signal. So I'm assuming that the bandwidth is something narrow. It doesn't have to be exactly, it could be information bearing, but information is in a very small bandwidth compared to the carrier, right? All right, so if the signal is spread over, only thing is, that's a good question. You will not remember here, still it will be a time delay. This is still true. But time delay won't come out as a phase delay. Of course, then what you do is if you go into the Fourier transform, you can push this time delay outside. But except there, the frequency will become not a single number, but it will be frequency dependent. So you can go into the Fourier domain and do something similar, wideband. Or if you know you can do the, remember what phase shifting doing, what the phase shifting is, shifting it back to make the signals coherent. So if you know where it is coming from, you can compute the delay and shift it back and make it coherent also, physically. Like you assume a model, or you go do it hypothesis testing, saying assuming it is coming from there, then I know the path, so I know how much will be the delay. So just delay it back, the received signal, that would be the, if that is the only signal, and if you do it for every conceivable location, at the right location, it will pop up. So that's called a ray tracing in EMT. We can do a similar idea here also, or you can go, so these are all signal processing techniques. But if you substitute it here into this expression, look at here. So I'm going to substitute RXX, this expression here. So this becomes A transpose theta. This becomes P A theta naught transpose. And then sigma squared I A theta. A theta is the general angle. So source is coming from here, you are looking somewhere else. That's what it is. So this will simplify. I'm going to do it in my head, but you guys should make sure this is right. So let's say the A is already unit length, so I'm going to divide it by, so this will be A transpose A will be 1, so it will be just sigma squared. But notice this is two different angles. So if you do this, this will turn out to be omega minus omega naught, right? If you call sine theta to be omega, then this will be omega minus omega naught. Right, we went through this last time, right? This is the beam pattern squared. The m goes inside, plus sigma squared. So what do you see? When you plot it, what do you see? Where is this pattern going to peak? Anyone? Huh? Theta equal to? So that's where, so remember what is going on. Theta is our steering angle. We are steering at different directions. And the source is located at, so I hope you see that when you plot this, you're going to see theta equal to theta naught, this is going to peak. But you will have the side lobe structure, and the whole game is to minimize these things, right? And you have the noise floor here, right? I think I did this right. Any questions? You know how this is done, right? We went through this. This is summation e to the power j I omega minus omega naught. Omega is pi sine theta. I just substituted it. And we went through this, right? I equal to 1 through m minus 1 squared, right? Last time. That's this expression. Or 1 over square root of m. Absolute value squared, right? So this, so you can see the beamformer also peaks at the right place. Now what if they, remember as I said, most of the scene is never going to be just one signal. What if you have a multiple signal scene and you have, so you have a lot of things, and if you, this is your desired, so this is the general problem. This is the desired signal. And so if this is the desired signal, all these are interferences, right? So then the question will come, adaptive beamforming is like saying, you want to have the cake and eat it too. You want the gain to be maximum in this direction, and at the same time you want to minimize the signal coming from everywhere. Look at here. There is some, the signal is being received from other directions also. So if this is very strong, it could even kill this. So we want to, but we don't know where it is coming from. That's the whole idea of adaptive, right? You need to, so this is in a sense learning, or you need to sense the array needs to sense the environment, or the algorithm needs to sense, and then if it figures out that there are interferences, then you want to suppress it. So let's see how to do it and what's the idea there. Right? So in this one, so once again we will keep W of t as the weight vector. So the weight vector is unknown. So then remember we had the output is still y of t. Output is y of t. And if you look at your expression, y of t is W transpose x of t. And the output power is W transpose RXXW. In other words, the expected value of square of this, right? I simplified it for you, YT squared. That's W transpose RXXW. So in the adaptive, so this is still true. If you're using weight vectors, this is the output. So of course, if you look at here, if you have desired signal coming in, and you also have things coming in, you have a lot of power coming in. So we want to keep the output as low as possible. That's the strategy. Because if you keep the output power as low as possible, hopefully this unwanted signal contributions will be minimized. But you have to do it under constraint, because if you just say I want to minimize the output, then the best one is put weight vector equal to 0. So while maintaining the gain along this direction to be constant. So here the strategy is minimize the output P bar. So the output power is W transpose RW, right? See, this is the output power subject to the gain along this direction. So remember, the gain along this direction, we went through this. If you use a weight vector W, the gain is going to be W transpose A theta not equal to constant. And the minimizer, of course, the free parameter is not Rxx. The free parameter is W. So we need to do this optimization problem. So to do this, I'm going to make so this is a constraint optimization. So I'm going to bring in a Lagrange multiplier to attach this. So that's going to be lambda, some parameter, W transpose AF theta. Because this could be complex, I'm just going to add the complex conjugate also. It's one and the same thing, right? Remember, all these are vectors, right?
Why isn't theta anywhere here? Why isn't theta anywhere here? Because like it seems to me that minimize it over all the thetas, right?
No. So this is the weight vector, of course, is a function of, it's a is going to be is that what your question is? So remember, again, look at the problem. For whatever reason, you decided that this is my desired direction, theta naught.
Yes.
And
you want the power in that direction.
To be what?
You want the power
in that direction, but I'm going to steer the whole, I'm going to look at an arbitrary angle, right? Because I don't know what that, so I'm going to, so we'll see if you know that, so the gain along that direction you want to be as high as possible, right? So this is the gain along desired direction, right? So you're trying to find out weight vector W. Gain along the desired direction, maintain that to be a constant, or as and at the same time I'm going to minimize the output power. So you can see if the source is along this direction and that direction is unhurt because I'm keeping it constant. So the only way you are going to minimize is by logic. You must be minimizing the contributions from the unwanted signals or the interferences. That's the idea. So you are trying to approach this in an indirect way.
One other question is that, like,
but hold on. You understand here, because main idea here is I don't even know where the interferences are coming from. Of course, if I know the interference, you will say, why don't you put a null? That's what people do also. If I know a source is coming from a particular direction, we can try to put a null rather than you can say that gain should be 0. That is the null, right? So you can do that constraint also, you can certainly do. But generally, you wouldn't even know where the interferences or the interferences could be running around, right? Yeah, what was the other question?
Don't we have a power constraint as well? So like you cannot put like all the power you want in that like base, right?
Remember, there is no, this is passive, right? So we are not transmitting anything.
Well, like if you fill in everything, it becomes a transmitter as well.
I know, it is true. You can use the same ideas for transmitter also. Remember, power is whatever is your battery is going to provide, right? Or klystron is going to provide. So the question is, how do you want to pump the power into space?
So it means that like the norm of these W's should be sort of bounded, right?
It should be parametered, right? So if you say that I want to pump all my power in this direction, generally, of course, usually if I'm looking in this direction, I want to pump right now all the power in this direction. When I look in this direction, I want to pump the power in this direction. So that will be precisely exactly the same problem, right? So we can use all these weight vectors for transmitter also, right?
Yeah, but like if you get like the norm of the W to be, I don't know, 10,000 and you cannot afford that much power in the W, then...
Yeah, remember, this is only a... the source has to, look at it the way it is. Source is going to be connected here, then the power goes and gets distributed in such a way, it just coheres here. So this is only like a tubes, right? To whatever, the source is here. So if you have a small source, then...
Yeah.
Right, in other words, these are not active components, right?
If you want to use it for a transmitter, you should do RXX to be sort of like whatever power it has.
No. RXX is still going to be... I mean, first of all, if you go doing it for transmitter, you could say the general way it is transmitted is you transmit it spherically so that it goes all over, right? Right? If you have a dipole or not even dipole, a single monopole, the power is going spherically, right? In a dipole, you still get some direction, right? So, or in the transmitter case, all you can do is if you know a desired direction, then you can pump your energy in that direction simply using beamforming, you can see. All you need to do is electronic steering, right?
Yeah. So, sir, the wave vector we are designing is you will know or something?
What is it?
The wave vector
Yeah.
design is it of you will know?
Weight vector, look at here, weight vector, we already put a condition here, right? So this is of unit length. And we are saying weight vector should be such that this should be equal to a constant, whatever this is, right? So this constant I can change. You can see from Schwarz inequality, you can begin to see the constraints on W also, right? This is unit length, so W star is less than or equal to 1, right? Already there, right? And so I think a couple of ways you can do this. The way, because of it, this is all vectors, and I want to do the minimization on W. Let me, the way I generally people say, let me take the derivative with respect to W, that, then it becomes a derivative with respect to a vector and so on. Rather than that, look at this. I'm going to, maybe, I don't know whether I showed you this. So let me expand this quantity. So remember, we discussed about R half. R half is the square root of the covariance matrix. I went through this. You do UdV and the diagonal entries, you take the square root and multiply it back. In any case, R half multiplied by R half is R, symbolically at least. What is it?
Why do you have?
Why do what?
Why do you have
Two terms? Well, remember, as I told you, this may be, this is complex, right? So the dot product is going to be, so I should probably put it this way, it could be complex. And this is already real. Look at here, this is real, right? So to make this a real thing, I take the, because this complex conjugate is exactly the same condition, right? So adding it is not going to change anything. It's just that to make the algebra. So if I expand this, this is going to be R half. Remember, this is XX star, right? Because this is norm squared. So this is going to be R hat.
Professor, your condition is
What?
I mean, the condition is W is log, but in the logarithm you are using.
Yeah, all right. So if you want, you can put theta naught also. That's the desired direction. Or here you can take out the theta. I only put theta naught there just to get your mental picture ready. But theta naught maybe, I will be changing the theta naught because generally look at the, when you look somewhere, you don't even know where the signal is coming from. Theta naught is wherever you are looking right now. But little later I look here, etc. So we could have, you can put theta naught, or let's do this. Understanding is that theta is where you are looking.
We need minus 1.
What?
We need minus 1. Yeah.
Minus here?
I mean minus 1. The condition is the W A here.
Oh yeah, you can put minus 1, right? Yeah. Right. Then I don't know whether I showed you. Look at here. This whole thing is, I'm going to call a vector y. Then its norm squared is y star y. So I'm going to do y star first. Y star is w star r to the power half. R is conjugate transpose minus a theta naught star r to the power minus half. Then I should multiply by y. Y is r half w minus r to the power minus half a theta. You don't need a 0. All right, so if you expand this, you get 4 terms. Look at the W transpose, so you get W transpose RXXW or minus W transpose. Here R half and R minus half cancels. So you get A theta. So I'm getting back this term. And if you do this term, this and this cancel, so you get minus A star theta W. And the last term is A star R minus A. So if I from there I can get you can see that's very close to lambda. So look at here. These 3 terms, this term, and this term are here. So I'm going to put I guess I should have put a lambda here, right? So let me put a lambda here. So I have a lambda here, lambda squared. Okay. So you see that this term are here. So I can write the lambda as R half W minus lambda R minus half A theta naught minus all right, then you remember this is supposed to be minimization on W. Now the answer is very clear. This is the only piece involving W. So if you want to minimize, this piece should go to 0. Then you can solve for W. So you need a R half W equal to lambda R minus half A theta. So you can solve for W is lambda R to the power minus half A theta. So the question is, what is lambda? There the constraint is going to help us. So the constraint says W transpose A theta should be 1. But W transpose is, look here, A transpose R inverse from here, right? Lambda A theta, this should be 1. So we can solve for lambda. Lambda is 1 over A transpose theta R inverse A theta. So if I put it in here, you get W to be you get this solution. So this is not, so you can see this is extra because look at here, beamformer it was just A was the solution. So here you are doing some suppression and things like that. And finally, if you look, so I'm going to call it PC. C is for Capone. So you just need to, so output is going to be W transpose RW. So we substitute for W transpose is going to be A transpose R inverse from here, multiplied by R, multiplied by R inverse A, and the denominator is A transpose R inverse A, A transpose R inverse A. See, this is identity. So A transpose R inverse A cancels, and you get this classic result. So this is the output. See, in the previous case, it was just A transpose RXX A. So the Capone output is going to be 1 over A transpose theta. So what you should do is go home and do a 1 source and 2 source. I'll show you how the covariance matrices are and simply plot it so that so the question is, which among this has better resolution? So See, I am plotting two methods here, okay, two outputs. This is one output, this is, so which method, there are two sources here. Look at it, this is obviously a mock diagram. Two sources at theta 1 and theta 2. But when you look at the output, one output is like this. Another output is like this. So which one has better resolution? Anyone? The second one, right? Yeah. So the ability to resolve closely spaced sources is then you say the method is better or more powerful. So we want to see, so between the, so you can see, if you can show that, so let's see between these two. So you have, of course, R half multiplied by R minus half. So if you multiply R half with R minus half, what do you get? Identity for any R, right, including this. So let me multiply by A transpose here, A here. So A transpose A is 1, so that's also 1. Then let me call this to be C, and this to be B transpose. Okay, so B is R half A. C is R to the power minus half A. See, now we know this is positive, right? We don't need to, because we started with A transpose A. So now we can use the Schwarz inequality on B transpose C squared is less than or equal to B transpose B multiplied by C transpose C. So let me substitute for B and C. So B transpose C is A transpose R half, then R half A. And C transpose C, C is what? A transpose R inverse A, right? So we get the identity that, so we get this. From here we get, so this is C transpose C. Remember, these are vectors, right? So from here we get A transpose RA is greater than or equal to 1 over A transpose R inverse A, right? Because I just took this term to the other side. But look at here, this is PB, this is PC. So it is clearly showing that PC has better resolution, because this picture must be like this. PC is always below PB. That's what I just showed you. So a situation like this could happen, or both could resolve. But if this resolves, this will definitely resolve. If PC resolves, doesn't mean PB will resolve, because you could have a situation like this. So that concludes that the second method has better resolution compared to the first method in a quick manner, right?
Could you repeat the argument? Because what if PC was much larger?
PC won't be larger. PC is always, look at here, PC is always below PB.
How does that show that the resolution of PC?
No, I'm not saying it is showing directly. But so pictorially it has to look like this, right? Whatever is PB, PC has to be below that, right? So here both are resolving. So you could have a situation, PB is like this. This is PB, this is PC, right? Here you can, this has to be below this. So it could be like this also. But it could be, if there are two sources, it could also be like this. So you can see there is, when this has two notches, it's, this will most likely have it. Even though this argument doesn't provide, this gives you a flavor, that's all I'm trying to say. Now if you want to clearly see it, the easiest way is you start, so let me give you this as a homework. You do this, so let's do a, remember for single source I already gave you, why don't you, so let's take a single source. So R is of course P1 A theta 1 transpose plus sigma squared I. This is for single source. So what will be interesting is two sources. So R1 is, you'll have two terms like this. So remember, you have either one source or you have one more source. This is the case, right? So here R2 will be P1, A1, A1 transpose. Just to make notation simple, A1 means A theta 1, okay. This is A1. Plus P2 coming from a different angle, A2, A2 transpose. Plus sigma squared I. So what you could, you have R, you know the weight vectors. In fact, you know PA, PB, and PC. So substitute this R and plot this for different values. So say take this to be 50 degrees and this to be 60 degrees. And in another case, you take 50 degrees and 55 degrees. Most likely the beamformer, so what I want you to do is plot the plot beamformer and the Capone output. You can also do this by hand and see the resolution. So I already did this one for you, right? So PC would be what? PC, you have to invert that matrix, right? So the rank 1 inversion is easy, right? So you have to look into some books and see how to find out R1 inverse. Remember, you need R1 inverse here, right? So these two are easy. Otherwise, I'll give you the formulas for invert. Invert, then multiply by that, so there will be few terms. And this one, there is no, for the PB, there is no inversion. You just substitute these. So this you can see here. PB you can already see, right? That PB will be all right, so in general, in fact, PB will be, you can say, if you have K sources, it will be like this, right? You should be able to see this right away, right? Everybody sees this, right? You substitute it. So here you can see, if you plot this, you have one source like this, one due to one. The other pattern is like this. So if these two peaks are close enough, you can see, you will see only a single peak. So you just have to plot it and to see. Whereas in a situation where these peaks merge, the PC may not merge. So you can resolve the signals. And you can see the logic. This is a better method than the other one. Here you are saying, I am trying to only look in this direction when other things are not there. Hello?
In the